In this video, I'm going to talk to you about stationary waves. So far we've only learned about progressive waves, and progressive waves are waves which transfer energy, whereas now we're going to look at stationary waves. And stationary waves are also called standing waves, and stationary waves store energy, and that's something that we're going to look at during this video. So when we're looking into stationary waves, what I'm going to do is I'm going to put a stationary wave onto the screen so you can see what one looks like. So I'm just going to put two ends here. I have a dotted line going down the middle. I'm going to draw one wavelength, which looks like that. So hopefully you notice that that's one wavelength of a wave. Now for a stationary wave, that wave doesn't move, so the energy is not transferred across. So actually how you would observe that is you would see the wave looking something like this, because it oscillates usually too fast for us to notice it changing. There's points on the wave which don't move, which are these points here. Okay, and those have zero displacements the whole time. The particles that are there don't move at all during the time that the wave's set up. So we call those points nodes, and they're regions of zero displacement, and their amplitude would be zero because those nodes, those points, do not move relative to the rest of the wave. The reverse then, the parts where you have the maximum amplitude, which is this bit here. Okay, I apologise about my drawing. You would get antinodes, and those are points of maximum displacement and maximum amplitude. The other particles, so if we just choose a different particle in this region, which I'm just going to use yellow for a second. Okay, so this bit here, those particles here would move between those 2 points only, and that point there would be their amplitude, but they don't go past the maximum amplitude which you find at an antinode. Now, as I went through that drawing, hopefully you noticed that I've only drawn one wave there. So one wavelength is the full thing from side to side. And notice then that the separation between the two nodes, so if you go node to node, that is half lambda. And if you went from an antinode to an antinode, that would also be a half lambda. And I guess the final thing to say that if you're going from a node to an antinode, that would equal a quarter lambda. So how do you form a stationary wave then? Well, to create a stationary wave, two progressive waves of the same frequency need to travel in opposite directions, and those two waves will then superimpose and interfere. On the diagram here I've got a blue wave travelling along. That's reflected, and the reflected ray will be what we would notice as a red ray. Now, in this diagram here, this is the actual component of what happens when we've got superposition after superposition has occurred. I'm not drawing the waves as they're superimposing. But what you should notice, or should be aware of, is that when the waves meet in phase, they constructively interfere, and an antinode is created. Remember that the antinodes are these points here. Okay, and when they meet in out of phase or antiphase, so they're in opposite phase, a phase of pi, phase difference of pi, they would destructively interfere, and that's why we get the nodes, which are in these positions along the rope there. So here I just want to talk to you about how the particles will move in a stationary wave. So you can see on the diagram at the first bit we've got a stationary wave that's here. Okay, and it's moving through this pattern there. What's going to happen to it next in that quarter of a time period? The particles that are in this half, this bit here, will move down to the middle line, and the particles over this side will move up towards the middle line. And then the wave you would be left with would be just a wave going straight across here like so. So you wouldn't actually see there's no displacement of any of the particles. In another quarter of a time period, or after half a time period, what happens is those particles that are along the stationary line here will then move down to have the opposite wave to before. So the ones that were at maximum amplitude and positive displacement will be now at negative maximum amplitude, and the ones that were to start with at negative amplitude will now be at positive as shown there. And so the wave you're left with is the red line as shown there. Moving on to the next one. So moving back on to where we were to begin with, if you remember correctly, this is the place that we were after half a time period, so the red line representing the half time period. What we're looking at now is where the wave moves to in 3/4 of a time period. So it started here, so the particles would have been aligned like so. What happens over the next time period is the quarter of a time period is those particles will move upwards here, these ones will move down, and the wave would now be along this black central line again. So after 3/4 of a time period, the wave would all be along this stationary line here. Moving on to what happens in the final quarter of a time period then, is we remember we're starting at the black line. What we're looking at here then is that the waves in the central line will move back up to their maximum position where they started at the beginning, and the waves down here will move down to their maximum amplitude in the negative direction, as they were before, right at the start. We're just going to quickly look at stationary waves on strings. So as I mentioned before, to create a stationary wave on a string, you'd first of all put the string at a constant frequency. The wave would travel down the string and then reflect off one of the sides, and then the two waves from opposite directions with the same frequency would superimpose. For waves on a string, what you need to be aware of is that there's always a node formed at that end and a node formed at that end. So any of the fixed points will always form a node. And these are the different frequencies that we have on stationary waves. So to begin with, we've got the fundamental frequency, which is also called the first harmonic, and that is the simplest waveform you can have on a string. So notice there's a node at either end, and then you've got an antinode and centre. And that way, you'll notice that that's just 1/2 of a wavelength, so L is equal to a half lambda. Moving on to the first overtone on a second harmonic, you set up your one wavelength here. Okay, notice that this time you've got 2 antinodes and 3 nodes. In this case, you can see we've got one wavelength, so L equals lambda. The second overtone, or the third harmonic, has got this wavelength here, so you've got a wavelength there, and you've got another half on the end, so that's 3/2 lambda for L. Notice this time you've got 1, 2, 3 antinodes, and 1, 2, 3, 4 nodes. This pattern is repeated again for the third overtone, or the fourth harmonic, where you've got 2 wavelengths there, and again 1, 2, 3, 4 antinodes, and counting the nodes, 1, 2, 3, 4, 5 nodes. This will repeat in the same format where you just add in an extra half of a wavelength each time for the fifth harmonic, and so on and so forth. That brings us to the end of stationary waves on strings.